Welcome to the Copper Spice YouTube channel, and thanks for joining us. In this video, we are going to talk about typedefs and casting, and explain when to use them and when they do not work. Declarations and type conversions. Programmers often use a typedef without knowing how they work or what they actually mean. We have seen developers use the name of a typedef by accident, and since the code works, little thought is spent on where the typedef comes from. Understanding typedefs can help you identify when they are useful and, more importantly, when they are required. One of the best ways to study typedefs in C++ is through examples. In this presentation, we are going to show various corner cases to illustrate a few things about typedefs, dereferencing, and typecasting.
Declaring a typedef creates an alias for an existing data type. There are two different ways to declare a typedef, and although the syntax is different, the effect is exactly the same. The version which actually uses the keyword typedef is the older form. In some cases, this syntax can result in declarations which are very difficult to read. In modern code, the syntax with the using keyword is preferred. There are also some cases in template code where the typedef keyword cannot be used because of parsing issues, and the declaration must be done with the using syntax. The effect of a typedef is to add a new name for an existing data type. It does not create a new data type or add any new behavior. The new name is simply an alias for the other type, and the two can be used interchangeably. After the program is compiled, there is no distinction between the two names. One of the main reasons to use a typedef is to provide a shorter name for something like the instantiation of a template. In this example, we are declaring stringlist as a short name for stdlist stdstring. We have shown both the older and more modern syntax. Another advantage to using a typedef is when the underlying type might need to change. If we decide to switch and use a vector instead of a list, we only need to modify the typedef and nothing else. To represent the size of something, we need to be careful to choose the correct data type. It is important to be aware that the size data type is platform, container, and allocator dependent. This is where a typedef can be extremely valuable. There are user-defined typedefs, but there are also typedefs which are provided by the standard library headers. If you want to add your own typedef, keep in mind that you cannot alter the declaration of the built-in typedefs. The typedef std size t is intended to represent the size of an object or the total size of multiple objects. The actual type of size t is platform dependent. It is guaranteed to be an unsigned integer big enough to hold the size of the largest possible region of memory. This is a generic typedef and is not associated with any container or object. Each container in the standard library has a typedef with the name sizeType. We are only showing the one for stdstring. The size type for a vector of characters would be stdvectorchar sizeType. Here is an example of some code where you may not have considered the appropriate data type. We have a string named var, and we want to declare a new variable named len, which stores the size of the string. The question is, what data type is the best for len? The most obvious answer might be int, but is there a better choice? There are multiple answers to this question, and we have listed a few of the possibilities. The first one we have is stdstring sizeType. This option is good since it exactly matches the signature of the size method we're calling. The stdstring class provides a nested typedef called sizeType, which is guaranteed to be the correct kind of integer to represent the size of a string on the current platform. The second typedef is declared in the class stdallocator_traits. The third typedef is declared in the class stdallocator. Neither of these are a good choice since both are intended to be used by the maintainers of the standard library. The fourth typedef should not be used in the case where your code instantiates the string with a custom allocator. This is because the custom allocator is not required to use std size_t for its size type. The last option uses the keyword auto instead of a typedef. The compiler will deduce auto as the correct data type, so this is a decent choice. We tend to discourage using auto too freely since it can make code a bit harder to read. Some coding standards would require auto here, and others would prohibit its usage. The choice to use auto is not actually about correctness, and that is subjective. We want to be clear in our evaluation. For std_string, all 5 of these options will evaluate to the same actual data type. If we change the container to an std vector, or use a custom allocator, then this premise may not hold true. For a consistent style which works with all containers, the first option is the best choice, and usually the most readable.
In this example, we have 2 declarations involving var1 and var2, both of which are declared using QString. The API of the QString class is very similar to stdstring. Let's consider a few questions about these variables. What is the exact value of var1 after line A has been evaluated? Although this example is a bit contrived, we did encounter it in some legacy code we were reviewing. What confused us was why var1 was declared as a pointer. Is this really necessary? So how would you explain the steps to evaluate line A? The compiler evaluates line A in a series of steps. First, var1 is dereferenced to give us the value April. Then the assignment is done. This assignment looks rather strange because it sort of seems like we're setting April equal to May. This is not exactly what is happening. In reality, when we dereference var1, we get a QString object. The assignment operator is then called on that object, which results in replacing the current value of April with May. Some programmers would say that var1 is a QString, which is not correct. The actual data type of var1 is a pointer to a QString. In this sample code, there is no reason for var1 to have been a pointer, and it only added complexity for no benefit. One possible reason you might need a pointer is if the QString needs to have a lifetime beyond the scope where it was declared. We are showing 2 different examples here. The difference between example A and example B is that the class QString is Unicode aware, while the class QByteArray is simply a container of 8-bit bytes. A typical usage of a QByteArray is to store the data read from a file or socket. In both examples, we are declaring an object of the corresponding type and casting it to a const character star. The question is, do these examples compile, and does either one produce undefined behavior? So it turns out example A does not compile. Depending on which compiler is used, the error message is often very vague and does not actually explain the problem. The best error message we found comes from a modern version of MSVC, which states, "There is no user-defined conversion operator that can perform this conversion." This is a very interesting error message, which might lead you to ask, what is a user-defined conversion operator, and what does it look like, or what role does it play in this code? Since var3 is an object, it is unclear what it would actually mean to cast this to a pointer. So if you compile example B in a current version of CopperSpice, you will get the exact same error as in example A. For some reason, the original QByte array class had a user-defined conversion operator, which is still present in the Qt implementation of QByte array. This conversion operator has been removed from CopperSpice since it seems somewhat awkward that a QByte array could be implicitly converted into a const character star. With the presence of this user-defined conversion operator, you can even omit the cast, and the code will compile and work. However, there can be a lifetime issue if the pointer is retained after the original QByte array has been destroyed. The syntax for declaring a conversion operator is a bit odd. The name of the method consists of the word operator followed by a data type. Since the conversion operator does not change the QByte array object, the conversion operator must be declared with a trailing const. Type conversions can be divided into two categories, implicit and explicit. The purpose of a type conversion is to change the data type of a given value. An implicit conversion is an automatic type conversion performed by the compiler. These happen all the time, and usually developers do not even think about them. Looking at the implicit conversion example, the compiler cannot simply copy the raw data representing the integer value 42 into the floating point variable. The compiler needs to convert the integer to a floating point representation, which is then stored in the variable. The other category is an explicit conversion, which is typically referred to as a cast. To perform this cast, you must tell the compiler what data type you want. In our cast example, we are taking a floating point value and casting it to an integer. In this case, the compiler will toss the fractional part and assign the integer value of 3 to our variable.
In example 4, we are defining foo as an std string with a value of ABC. The method call shown in yellow returns a pointer to the character A in the string foo. In the first sample, we are showing a C-style cast to a const char star. This cast actually does nothing, since the original data type the method returns is the same as the cast. In the second sample, the size of uint 8t is the same as the size of a char, and these are both primitive data types, so the cast is valid. So what about the last sample? Is this one valid? The fundamental question to ask is, can you cast a pointer to a const char to a pointer to a const vector of char? The string literal "ABC" is an array of chars. If you view the method call shown in yellow as returning an array of chars, you will confuse yourself. We have simplified the data types by removing the pointer and the const, which is actually what the compiler would do when evaluating this cast. So what we end up with is comparing the data types vector of char versus char. Since these two data types are not related, the pointer cast fails. Another item to consider is, what data would this pointer refer to? Since no vector is ever constructed, even if the pointer cast were valid, it would not point to a container of the correct type. For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching, and we hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.